Okay, great. Thanks for the invitation and thanks everyone for coming here. It's been really nice here. So I am sensitive to the fact that this is the last talk of the day and I want to keep it very chilled out. Please ask me any questions you might have. I want to go slow and steady and I love questions. So please ask them at any moment. This is also going to be joint with Will Perkins, who you've heard 2 talks by now already. So maybe this is a way to sneak in. Maybe it's almost another talk by Will, but I'll be delivering it this time. Okay. So I want to start not with the main object that I'm going to be talking about. I want to start with a slightly different perspective on something we've seen before, hopefully. So I want to talk about the ideal gas, this is particles interacting in space with no interactions. I want us to just think for a very quick moment, what would be a good mathematical model of this? We're going to do this in the continuum. And the best way to do this is going to be a Poisson process. So hopefully we've all seen a Poisson process. I'm going to just sort of redefine it very informally so we can really feel that this is an ideal gas. So I'm taking a set in RD. You can put this in a more general space if you would like to, and we might do that later. And I have an activity, or as Harris called this, we might call it a fugacity later on. And now each little box of dV is going to have a point in it with probability lambda dV. And I want these to be independent of each other. And this is a way to define a Poisson process. So notably, there's no interaction between particles. And that's the ideal part in ideal gas. And this is really going to be the most simple way to have particles that aren't interacting at all. So now once I start with this, I can ask, what happens if I add even the tiniest little non-trivial interaction to the particles? So this is going to give us the hard sphere gas. We're going to start with a bounded set in RD. Once again, you can work more generally if you would like to. I'm going to take a parameter R, which won't be very important, and an activity, which I will also sometimes call a fugacity, lambda. So now what I'm going to do is sample a Poisson process of intensity lambda in S, and I condition on no points being within R of each other. And now we call this the hard sphere gas or the hard sphere model, because I think about these as the centers of spheres that are not allowed to intersect each other. And these are going to be of radius R/2, the way I've parameterized it. And I have a very high-tech simulation for you here. Right. So this is what happens sort of in dimension 2. And now let's just think for a quick moment of how do we expect this to behave? So if lambda is small, then when I sample my Poisson process, I expect to not have too many collisions. It's going to be like fairly sparse. So maybe I expect not too much interaction to be going on if I do this. And here it should behave maybe more like a fluid or a gas. But now if lambda is really big, we expect our Poisson process to have lots of points. And then maybe, some might hope, a structure might emerge. So we've seen this sort of throughout the past day or so with things like the hardcore model. As lambda is increasing, we might see a structure emerging. When lambda is small, things are sort of vaguely independent of each other or correlations are decaying. So we have a few different ways to distinguish these cases. For now, one way to think about it is I just take 2 sets A and B very far apart from each other. And if the lambda is small case, I might hope the behavior on A is going to be roughly independent of B as the distance gets really far apart. And if lambda is very large, maybe it's the case, but we have no idea, that it does not decorrelate. And this is what we saw in the hardcore model on Z2, for instance. So I want to introduce just a tiny bit of history here. A lot more can be said, but this is a very, very basic model of a gas or any repelling particles in the continuum. I think I included some pretty adventurous applications, which are actual, and we do include these citations. But I mean, if you want to model sort of anything in the continuum that repel each other, so you can think like trees or stars, or even there's an application of time and place of earthquakes that use this model for something like this. It's like a very basic model. You're just asking for the most basic repulsion. It's studied by a lot of folks, including Boltzmann, who computed the first couple terms of what's known as the virial expansion, which I won't be getting into. This is a very old model in statistical physics. And the Metropolis algorithm, which is Markov chain Monte Carlo, was first used to sample this 2-dimensional hard sphere. I also just want to point out, while I was preparing the slides, I did look more into all 5 authors of this paper. I don't know if you've ever taken a look at what happened here, right? This paper is Metropolis and then two couples, all five of whom are physicists. All the five have very interesting Wikipedia pages that I recommend reading. And the two wives involved led the programming. These two husbands led some of the theory, and Metropolis paid for the computation time. At least that's according to Rosenbluth. It's a little spicy as to whether that's the truth. But, you know, it's pretty good. So the question, or at least a huge question, is do we have a phase transition for some D? So I haven't even specified exactly what a phase transition would mean in this sense, but we've seen a couple of notions over the past couple of days, and I may introduce a couple more, or at least review them. So I want to point out, we know in dimension 1 that this will not have a phase transition. This is a very general and broad theorem. If you have a one-dimensional system and it has only local interactions, then you will not have a phase transition. It turns out there's a more complicated thing happening in dimension 2. There could be a phase transition, but because you have rotation and translational invariance, a phase transition can only look sort of weaker than one might expect. Yeah. No, sorry. D is being fixed. R is being fixed. Lambda is the guy variant. Yeah. So we're always to think about R as being fixed, and everything here is actually sort of homogeneous. So I can fix R to be anything kind of nice you want. Usually we fix it so the balls have volume 1 or something. And lambda is going to be the parameter variant. Yeah. Any other questions? Yeah. 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 Certainly not obvious. There is a paper that I do not remember the name of the author for, but Will does. Yeah, recurrence. So it has been confirmed and proven explicitly in this case. It also is sort of a more general, like, field theory-ish idea that, yeah, but it has been confirmed for hard spheres. That sounds right. Yeah, it is not a. It's pretty chilled out. Other questions? Okay. So I want to think before we, say what we can prove. Let's think about why no one has proved a phase transition here. I want to compare it to the hardcore model. So on Z2, for instance, what we're going to do, just as a reminder, is I'm going to sample an independent set in a box with probably proportional to lambda to the I. We're going to take lambda small and lambda big. And the ground states here are what we call the densest independent sets. I have a very nice mathematical picture of what those look like. So we know that basically you either have all of these black squares or you have all of the red squares. So we have two extremely nice ground states, right, that are just extremely dense independent sets. And crucially, they're extremely far from each other. So we know for lambda small, correlations decay exponentially in distance. Sort of not even clear what name to put next to this. Is sort of ancient. And when lambda is large, we look like sort of a perturbation of all odd or even. And that's the theorem of Debrushin. Now, ground states for hard spheres become a much more complicated question. Right? All of a sudden, oh, it looks like there might be someone in the chat. Okay, Jeter in the video. Nothing to do about that. Okay, so we have optimal sphere packings here. And there's also another issue I'm going to return to in a moment, which is that we also have a lot of symmetry that we can apply to these ground states. So the only dimensions in which we know these are 1 and 2, which are pretty easy exercises. Dimension 3 is a theorem of Hale's. And I wrote 2 years down here because it was proven with computer-aided proof in '98 and then checked rigorously in 2017. And then Vyazovka in 2017 proved dimension 8. And Vyazovka and 4 other authors proved dimension 24. That's a complete list of the dimensions in which we know the optimal sphere packings. So I have 2 very nice diagrams here. Does anyone know what this is on the left, by the way? Out of curiosity. So this is Kepler conjecturing that this is the optimal sphere packing in dimension 3, and this is the Kepler conjecture. And on the right is something related to the E8 lattice, which gives us the dimension 8 sphere packing. So large lambda is going to be hard, right? Understanding the ground states and proving they're correct is already a very challenging thing to do. We expect in dimension 2 that the phase transition is somehow weaker than it would be in maybe another dimension if it does exist. And thus, if we were to try to prove some type of a phase transition here, our best candidates might be 8 and 24. But even these dimensions, you have something that is a little bit more dangerous than just that the ground states are challenging. And that's that I can take any of these and I can just slide them over a little bit and I still have a sphere packing. I can also rotate them. On Z2, I have literally 2 of these. While here I have continuous families of symmetry I can apply to them. Okay. Yeah, notably, this is not the case in ZD. Okay, questions? Yeah?
Right. I guess, could you like define the model or
yes, we can go back to that, or I can state it one more time. Our model is we have a set in RD. Yeah. I have a radius R, which is not very relevant. I do Poisson lambda in my box, conditioned on none of them being within R of each other. And that's the model. I'm going to have lambda varying. Yeah. Great. Just conditioning on this. Yeah. Other questions? So this is also a good time to point out, this is a point process, but I think it's really nice to think of it as a continuous version of a spin system. It's going to behave very similarly with conditioning on boundary conditions. It satisfies this so-called DLR equations, which is like a domain Markov property. And in some sense, it behaves more like a spin system than other families of point processes you might have seen in probability. Okay, so what can we actually prove? Let's talk about maybe a slightly more general setting. So a classical gas, which is also a Gibbs point process, is now built from just 3 ingredients. I've got a bounded set. I'm going to have a pair potential, which is just a function from RD to the positive, non-negative numbers plus infinity, and an activity lambda. So for a finite set of points, I'm going to define the energy associated to them as just adding up the pairwise energies. And I'm cutting out the diagonal. I'm not going to have any nonsense with that. So the classical Gibbs point process now has density e to the negative energy of this configuration against this Poisson point process. So now you can think, rather than conditioning on them not to intersect, I'm going to pay maybe a probabilistic penalty of some kind that is directly related to the energy that I have. So for I'm assuming that phi is repulsive, and I'm going to always do that. That means that this is a genuine penalty over here. Nothing like this is assumed. Yeah. I will need some assumption. Maybe it's, for now, we can think about it being a finite range. We will relax that to something in a moment. So the hard sphere potential is just the one that says my energy is plus infinity if any 2 are within R of each other, and it's 0 otherwise. And this is just going to say when I take e to the negative of this number, I'm just killing anything in which I have 2 points within R of each other. As long as it's positive, as long as my energy is positive, it's still repulsive because I'm still paying a penalty for points being close to each other. Yeah, I guess that's true. For lambda extremely large, this might be the case. Yeah, it's true. So this is, I understand what you're saying. This is the convention, like Ruel's book, for instance. Yeah. Yeah, but that's an excellent point. Yeah. So in some sense, it's like Poisson plus repulsion is maybe a way to think about it. Well, you could think about it as nearest neighbor in the sense of, let's say phi is just supported in like a ball. Then I'm going to have just only interactions within that ball. And it might vary how strong the interaction is depending on where they are relative to the point. Yeah. Yeah, so you're going to interact with more than 1 point. Yeah. Yes, correct. Right, yeah. But you can, in fact, interact with more than 1 point. Yeah. I don't know if I would say that. I mean, you're still only interacting locally in Euclidean space. And you still have a domain Markov property in the sense of a condition on a boundary condition. I can resample the inside condition on that, and it's just going to be another Gibbs point process. Okay. So we're going to define our partition function here. This should look sort of familiar. Rather than looking at a count over configurations, we're going to look at some sort of volumetric count here. So I'm going to sum lambda to the k over k factorial. This is sort of my term coming from a Poisson process here. And then I'm going to take the volume of sort of these configurations of k points where I'm weighing them by the energy associated to it. And now I wrote this, it's sort of a little shaky, but the idea is the probability that I have a given configuration is going to be like this probability here. So this is like sort of the normalizing constant, and this is the density. And this k here should be number of points in X. And now we can define the pressure, just like we saw in Will's talk, for instance, as a limit if I take increasing sets in a sort of chill manner. Let's say my sets are just going to be boxes of log partition function normalized by the volume. I also, yeah. Oh, it depends on what field you're in. In my field, that doesn't really make rigorous sense, but it is, yeah. Yeah, so it is true, yeah. So I mean, if I'm fixing and I'm looking only on points of a given size, then it's like a literal equality, yeah. I'm comfortable with dx being written without a squiggly inequality in general. So I didn't go through it earlier, but I want to point out we have pressure, we also have a volume. You can look at the number of points. And if you apply this to the ideal gas, you can prove PV equals nRT. Of course, there's no T or R because we're mathematicians, so these are just constants. But you get the proportionality that you would want. So a meta theorem, which in some sense is a genuine theorem by Yang and Lee, says a phase transition is a point at which this pressure is not analytic. So this is, in some ways, a definition. In some ways, it's a theorem. And in some ways, it's also a little confusing what this analyticity here might mean. But we should think about any example of phase transition that we all know and love. So maybe the best example that we understand the best is percolation. And if I look here at the probability, let's say a vertex is in the infinite cluster, in let's say Bernoulli percolation, the picture looks like this. And what's going on here is I'm going along in a nice and chill analytic fashion at 0. And then I do something non-analytic and I continue analytically. The idea is that you can think about this as just saying, well, the main physical quantity I'm looking at, let's say the pressure, is doing something non-analytic. It might not be continuous, might not be differentiable, it might not even be analytic, but it could be smooth. You could have lots of different possibilities here. Okay, so what has been done? We're going to define this constant C phi, which we're going to assume to be finite. And in fact, this is the condition we're going to need instead of, let's say, finite range. And then classical results by Groeneveld, Penrose, and Ruel proved that if I'm looking at a classical gas with this pair potential, and let's say it's repulsive, then you're analytic for lambda being less than 1 over E times C. So in particular, we have no phase transition for lambda in this range. So for hard spheres, C phi is the volume of the ball, where I'm looking at, this is the radius of interaction, not the radius of the balls themselves. The idea here is to Taylor expand log of z in a clever way and I regroup terms. This is what's called the cluster expansion. And you show absolute convergence of this series. That'll end up proving analyticity of log z. So that'll end up proving a uniform zero free region for the z's. And that'll end up giving me analyticity Miller. Okay. So I want to note a couple of limits to these approaches. So log z being analytic means that I have z being zero free. And these approaches show zero freeness in a disk around the origin. But I just want to draw very quickly. Let's say this is 1 over EC. They prove zero freeness over here. And now the values we care about of lambda aren't actually these complex ones. We care about these real ones. So in some sense, if I want to prove analyticity, asking for a disk is sort of asking for too much information. Right? So phase transitions are about lambdas that are physically meaningful, which are positive. So in particular, those far from the positive real axis shouldn't correspond to a phase transition. And a fact proven by Gronvald and Penrose is that the closest singularity of this log z to the origin is on the negative real axis. And the way you prove this is that you look at the Taylor series and it actually alternates in sign, meaning that the first place it gets messed up is on the negative real axis. So we know if I try to expand this disk, I'm going to get messed up when I hit something like 1 over EC, and maybe even earlier. So they showed analyticity in this disk, and you can't push the disk that much further. So there's some other approaches. I didn't describe uniqueness, but this is uniqueness of infinite volume Gibbs measures. And Hoffer, Temmel, and de Ruyter prove uniqueness for 1 over C phi using a probabilistic argument known as disagreement percolation. Helmuth, Perkins, and Petty proved uniqueness using a path coupling approach for hard spheres. And there's this really lovely work by Michelen in the 70s who proved uniqueness for repulsive potentials up to 1 over C phi. So we can go up to here by Michelen. So the theorem I want to talk to you about now is if you give me a classical gas and a pair potential that's repulsive, then you have analyticity all the way up to E over C phi. I didn't draw this proportionally, but we can go up to here. And the picture I want you to keep in mind is we in fact prove a little zero free region in a neighborhood of this. So we know we're zero free in everything enclosed in what I've drawn here. Sorry, this picture is slightly alive in that this should be on the very tip of what we've proved, although that might change in a couple slides. So if you're thinking in hardcore model world, which all of us have been for the past day and a half, then you should think about this as the analog of Weitz's bound. And we're going to get there in a slide or two. So we think that delta is like C phi, and this is like E over delta. Okay, any questions on the mean theorem? Yeah. We'll get there. So yeah, definitively for any dimension of RD, it is not optimal. In some sense, it is optimal, but not for RD. Yeah. Hmm? Yeah, so I guess in some ways you can think about this. We'll actually see it in a moment why it will be relevant. But you should think of this as measuring the total strength of the potential in general. It's measuring how quickly it decays to zero, sort of in relation to the volume growth of RD. You can replace again RD with anything sufficiently nice, and the same sort of a thing is true. In fact, the theorem is verbatim true. But yeah. So you should again think about this in some sense as like the maximum degree of your graph. Yeah. All right. And the idea here is to work in a very tiny neighborhood of this positive interval. So we know that these other singularities that might exist could stop our approach, but they're not going to mess up uniqueness or analyticity. So we want to work as close as we can to this positive real axis. Okay, so I want to start with a very spacey view of the strategy, and then we're going to zoom in and get a little more concrete. So we want to do something similar to White's. And we take a lot of inspiration from White's. I will recap a couple of the main ideas in White's, maybe in a slightly different way than we've seen throughout the past couple of days. So our main inspiration here is I want to define some important statistics of our partition function. And we saw that in this White's approach, we look at these occupancy ratios, the probability it's plus over probability it's minus. We're going to define something analogous in our case. Then we're going to prove some sort of a recursion for these. So a lot of the time for White's, we phrase things on trees, but you can actually like completely ignore the tree in White's proof and just look at a certain relation you have between occupancy ratios and occupancy ratios of smaller graphs. And then we have to analyze this recursion and inductively prove that you don't get any of your statistics are blowing up. This is our general vague strategy and maybe a bird's eye view of White's. Okay, so I want to set things up now. So we're now going to allow our activity to be multivariate. So it's no longer going to be treating every point the same. So all I'm going to do is now just have a nice function. And now it can go to the complex numbers, let's say. It only makes physical sense if it's positive and real. But all I'm going to do is everywhere I saw a lambda, I'm going to assign a lambda, like a bold lambda, to a given point. And now I have a density here, which is a number density, is going to be like this bold lambda v times this ratio of partition functions. So for now, this is a definition because I said lambda is complex. Okay, maybe I want the second thing here. If lambda is positive, this is actually the number density of this process, meaning that the probability I have a point in my hard sphere model near you is going to be like this density times this volume. So another way to say it is if I look at the measure that tells me the expected number of points in my process, this is exactly the derivative of that density against the Lebesgue measure. Yeah.
How does this relate to if you define your process to be like a Poisson process with this intensity measure and then condition to not?
That's going to be, that will behave quite differently. What you're actually doing is defining a Poisson process with this intensity and conditioning on it. Yeah, so this is sort of taking into account the repulsion that's occurring. This is sort of like saying the probability you have a point near you.
Yeah. Okay, but this is
this is for the hard sphere model.
But
yeah.
This is if you take the intensity to do that lambda, then it
yes, is exactly that. Yeah. Mm-hmm. Yeah. Okay. So I want to show the recursion. I think that's what I have on the next slide. Yeah. Okay. So I have a recursion. I'm going to tell you to ignore the bottom half of it, but I thought I should write it down. So what we can prove is if I look at the density at a point for a given lambda, I can write it as some integral, e to an integral of other densities. And we'll see here exactly this quantity that came up in our definition of C before, maybe to answer Tim's question from before. And now it's not actually important what these densities are. I'll explain in a quick moment what they are. The only thing we care about is that in some sense, they're smaller than lambda. We can look at their definition in a moment, but we can think about this as saying, I've written down my density at V in terms of densities at other points for smaller lambdas. Okay. So I want to take a quick moment and write on the board just very quickly what White's does, so we can squint at that and see if it looks similar. So the quantity White's looks at is RV, which is probability V is in over probability V is out. And on a tree, you can prove the following. If I look at the root, it's lambda times the product of 1 over 1 plus R of, let's say, the ratios of the roots of its subtrees. This is just a direct computation for the hardcore model. And his main idea is that on any graph, I can do RG is a product of, I'm not going to tell you exactly what these are, but I now have some other, let's say W's, and I'm going to write lambda W's, some new boundary conditions. So I can write it as this product that looks a lot like a tree, but now I have maybe weird multivariate activities rather than my univariate one. So if you don't want to think about the White's tree at all, what he's doing is he's saying, I have this recursion, and I can force it to look like a tree because it satisfies the same thing. But what he's really doing is writing it like this and then analyzing this recurrence. And now maybe if you squint, you can convince yourself I've got a lambda in front of both. And now here I have a product. Here I have e to an integral. So it's of a sort of similar flavor. Okay. So this is a continuous analog of this version. Okay. So now we want to prove analyticity of log. That's the same as zero freeness of z. It turns out that the same as proving a uniform upper bound on this density. So our strategy is going to be to take this equation here, and I can imagine trying to just unwrap it over and over and over and over again, and hopefully show that if I keep unwrapping it, I'm not going to get anything too crazy going on. It's not going to blow up. So the recurrence is going to write a density in terms of densities for smaller activities. And I know if I look at the zero activity, then I have just straight up my density is zero. So I want to iterate the recurrence many times and show that applications of the recurrence don't cause rho to blow up. So the way we actually handle this is very similar to what Harris was talking about. We have to do a potential function argument. Okay. Any questions on this, this sketch here? Okay. Yeah. Ah, yeah. So we prove it for all families. Another way to think about it, in fact, is rather than looking at S varying, if you just think about multivariate lambda, I can now have lambda being zero outside of a certain set, and that's like changing S. So you prove this uniformly for lambda being multivariate in a neighborhood that looked like this little sausage I had in the picture before. Yeah. This is similar to saying you want to prove some sort of a bound for all max degree delta graphs. You want to think it's like saying I want to prove this for all multivariate activities lambda in my collection I'm looking at. Yeah? Ah, you mean rather than a tree? So do you mean if I keep unwrapping it, do you mean like what like space do I end up with, or what zero freeness do I end up with? You are in some sense having cycles. It's a little trickier. We have to get into what these multivariate lambdas are actually doing. So really what's happening here is this activity is saying points closer to V than W see a point at V and others don't. And if I do this in hard sphere world, this will end up meaning if I keep unwrapping, I will not have cycles. This means if I keep unwrapping this where my potential is the hard sphere potential, I will not have self-intersections. Yeah. Okay. So we saw that you have analyticity here, where I can go up to this so-called temperedness constant. And the proof uses only local information. Okay, there's no close quotations. I maybe want to put the quotes here, which says if I'm only looking at where phi is sort of interacting, then this is kind of the best you can do. there's a sense in which we make this rigorous in a follow-up paper. This also works in more general contexts, like Riemannian manifolds. And if we only use local information, there's a sense in which you can't beat this quantity. And really what this means is, okay, maybe I won't get too deep into what this means. So in a later work, we showed that you can replace this notion of C with some sort of continuous analog of a connective constant. So in the discrete world, the connective constant is the base of the exponential rate for which you have self-avoiding walks of length k grow like this number to the k. So a very nice work of Sinclair showed that if you can do the hardcore model up to, basically says you can replace the delta in White's with the connective constant. Let me prove something analogous here. It's slightly more complicated to define this quantity just because it depends on the potential itself, but it has to do with what Harris is talking about here. You get into how you actually unwrap these. So this also means, for instance, in each dimension of RD, you can do slightly better than E over C5. So we know in each dimension for RD, you can actually beat this bound here. Okay. Actually, maybe I'll ask, anyone have any questions on this before I move on towards open problems?
So you can define this for like if you wanted to go really far, you can define this for like any method. But okay, at least
yeah.
But do you expect there to be like examples of spaces where you get to like the phase transition actually ends up being
this E over C?
E over C, or maybe a slightly better one.
Yeah, it's a good question. In some sense, we kind of expect this to be true, although the space that we have that constructs this isn't necessarily super well defined. Yeah. You could sort of imagine it would be like some continuous version of a tree where you have at each point you're attaching another ball and another ball. But this isn't exactly a great object to think about. Mm-hmm. Yes. Yeah, okay, that's exactly right in the sense of as we take the curvature to negative infinity, this bound becomes E over C phi. That is true. Yeah. Yeah, excellent point. Okay. Yeah. Yeah. Yeah, I mean, yeah, it's a little complicated. What we're really going to do is, yeah, okay. Basically, what we're actually going to do is we're going to do like a sort of topological proof on lambda. So we're going to show that you can like sort of extend lambda provided you're in the zero free region. So yeah, I guess in some sense, we're interpolating all the way from zero in a line. Yeah. It's a little more complicated because it's not going to zero just like literally on a line. You're like squishing down in this weird way, but that's what's happening. Okay. In the remaining few minutes, I wanted to talk about some open problems, including a few having to do with the hardcore model first. So we talked about existence of phase transitions for the hardcore model. And we saw about this on ZD, and in particular Z2. And now I just put here two pictures I stole from the internet on two lattices that to me look, I guess, vaguely similar. Does anyone recognize what this is on the left? I know at least one person does. And what is this? This is the line graph of Z2. And this is Z2 I've added in diagonals. So the fact this is the line graph on the left means this guy has no phase transition by Heilman-Lieb, because hardcore models on here are secretly matchings of Z2. And on the right, you do have a phase transition, but it takes you 90 pages, and it was only done last year by Ron Pellet. So this is quite a bit of work. So we want to think about when we have phase transitions for the hard sphere model, but I think there's still like quite a bit to be done about understanding what happens even for the hardcore model. So we know if I look at the line graph of any graph, I have no phase transition here. And the line graph here just means at each edge I put a vertex and I connect ones whose edges were originally adjacent. This, by the way, is a really fantastic and beautiful theorem. This goes directly through understanding the zeros of the partition function. This is extended in a really beautiful work by Chudnovsky and Seymour to claw-free graphs. So as long as you don't have as an induced subgraph, literally this graph, then you have no phase transition. So it's not just some broader picture about the boundary being big. It also has something to do with local obstructions. There's also, for a different reason, no phase transition on the triangular lattice. This is proven by Baxter. This is the so-called hard hexagon model. And this uses some really like exact miracles to certain modular functions. So a general problem is find some more examples of non-bipartite graphs on which the hardcore model has a phase transition. And also, I mean, maybe it's a little rude for me to add this here, but also prove it has one. So I came up with a candidate, and maybe someone here could tell me this is either a good or bad idea. But for instance, let's say you take the free group on 2 elements, and I'm not going to mess with the group, but now I'm going to generate my Cayley graph with A, B, and now just AB. So it's almost like, you know, our good old-fashioned 4A tree, but I have triangles thrown in everywhere. Does this guy have a phase transition for the hardcore model? Sort of more generally, what if I do this with free group K generators, and I just throw in one triangle? And maybe in some sense, this latter one might be easier if K is like 10 billion or something, because it's really, really, really close to being a tree. Okay. So back to the hard sphere model. The question, yeah. Yeah. Yeah, that's true. Or, I mean, yeah, or you could perhaps go with uniqueness of Gibbs measure might also be okay. Yeah. That sounds plausible. Yeah. Yeah, so you're right. You need to do uniqueness. Thanks. Yeah. Yeah, excellent point. Yeah. So now let's think back to hard spheres. Does there exist a dimension for which you have a phase transition? If the answer is yes, probably the best places to go are dimensions 24 or 8. Right? And now what I think is really tremendous about this question is if you replace the spheres with cubes, this is still extremely challenging. We can't prove this still. So replace it with axis parallel cubes. Now we know the ground states, right? Because we know how to pack space with cubes. It's a little more complicated than you might think, because I can take layers of them and sort of shift them. So it's not totally obvious you should have a phase transition. But if you do, maybe it is the case that you can prove it. Perhaps in dimension 2 might be easier. You don't have rotational invariance, so Merwin-Wagner doesn't kick in. And finally, maybe for this audience, and we were talking before with Lewis, might be a good thing to try this on something like, let's say, hyperbolic plane. On the hyperbolic plane, you might want to show non-uniqueness of Gibbs measure for lambda function. Okay, that's all I have. So thank you very much. Yeah, for sure.
So for which things do we know phase transition?
For the hardcore, you mean?
For I guess for the hardcore.
Yeah, for hardcore, the complete collection of things we know phase transition for is maybe very tiny. I think we have ZD. We have various other bipartite examples, like trees. And we also know very recently this ZD with next nearest neighbors, as the physicists call it. Yeah.
And so the phase transition in terms of NLP.
So in the case when you're a nice and chill, like amenable thing like this, that's good. Otherwise, uniqueness, non-uniqueness is the way to go. So
what about like correlation?
You can also get into correlation decay. I think uniqueness, non-uniqueness is maybe the easier way to think about it.
But I mean, is it known that this corresponds?
Sorry, lack of correlation decay would imply an existence of a phase transition in the uniqueness, non-uniqueness sense. Sorry, Tom had a question first.
If you're looking for
But this is true, you think, even for the hardcore model? Okay, thanks. Yeah, I'll look into it. Yeah, so what's really fascinating is if you take D very large, what do you expect sphere packings to look like? And the answer, the actual nature of this is pretty confusing, but we expect them to actually be disordered, in which case it's not obvious what we expect to happen for hard spheres in very high dimensions. Some believe that there's a sort of glassy phase transition for high dimensions. This was cited actually in Parisi's Nobel Prize as part of his work. Yeah.
It's also the case, like, maybe this is sort of what you just said, but like the things that are known are like you have very ordered ground states, and isn't it sort of expected that in other dimensions there are not like the ground states are?
Yeah. So I think yeah, it's true. Yeah. Yes. Yes. Yeah, we could do we can talk more a little bit offline, but we can do a deterministic quasi-polynomial time algorithm. It would be very interesting to make that actual polynomial time, but I think the issue there is not in the zero-free type approach. It has to do with high volumes. It is similar to that. Yeah, it's a Barbanock style argument with the cluster expansion, and you approximate the cluster coefficients. We can also do heat bath mixing in n log n time. So Will and I have a paper on this. Will finished a paper recently on a perfect sampler using the strong spatial mixing that we derived from this as well. Other questions? Thanks.